We will now go on to a chemical engineering course, which will be presented by Dr. Mohamed about designing of a course for a sustainable future. So I'm hoping that these three presentations today will stimulate a lot of questions, but more importantly, stimulate, again, thinking together, sharing together, and all of us then implementing locally. So Dr. Mohamed, would you like to take over?
Thank you very much. Can you hear me and can you see the presentation okay?
Yes, we can.
That's great. Thank you very much. Well,
just talk a little louder.
Okay, my name is Mohamed Hassan, and I was privileged just before the start of the pandemic to join Southampton University in a new venture of starting chemical engineering course to meet the sustainable development needs of the future. And this got me thinking over the last 2 years of how do I optimize the course in terms of the sustainable development goals here. And the first element that we needed to understand was to look at the value of education and what does education mean and how is education is formulated. It's about understanding the historical legacies to shape the future, basically. And within that, we had to address the Millennium Goals in terms of sustainable goals in terms of the resilience, the change. It's no longer just about the efficiency and the optimization. It's about the continuation. That's the word sustainability. And for that to achieve, for us to achieve that, we had to understand this concept from Charles Darwin as well, in terms of it's not just about the skills and knowledge management and all the different aspects of society that we have here, but it's about the resilience to change and responding to change here. And we all understand the breadth of sustainability in terms of it's covering the poverties, the hunger, the medication, the equality, the industrial impacts, the economical impacts, and the impacts on the land. But to actually apply that understanding in terms of the Millennium Sustainable Goals is to break it down into this diagram where we start addressing the biosphere as the largest element, the global situation, and the society links within the biosphere and how that interacts with each other. And then the economy is the factor of society that helps sustain society and helps the prosperity and success and advancement of society here. And within that, the integration of the industrial partnership. And this gave us an entire mentality on how we should move forward with a sustainable educational system for chemical engineering that integrates the three biospheres in terms of the three spheres in terms of the biosphere, the society, and the economy together in a new course that takes chemical engineering to a new realm. And then we started understanding what the SDGs mean in general, and we started looking at the educational accords, and we looked at the UN and the UNESCO kind of environment and mentalities. And it's all about embedding the sustainable development goals. It's about being aware. It's about developing the knowledge skills. And the two previous speakers before me have already alluded to this in terms of the table that the colleague was establishing and what they've done in the dental school. It's to actually engage the individuals with the fundamental principles of sustainability for them to actually understand what it means and then develop the legacy of education from the historical development into shaping the future in a better manner. So before I move forward, I just want to give you the latest definition according to the Institute of Chemical Engineers and the Engineering Council about chemical engineering. And it's the application of science and mathematics and economics in converting raw materials or chemicals into more sustainable forms here. And chemical engineering, historically, it's all about upscaling the raw material, first of all, designing a process that will change the building blocks from the raw materials into useful products for society. So at the core or the historic legacy of what chemical engineering is, it's all about transforming the raw materials into the fundamental building blocks, and that's upscaling the raw material. Then we design a process around it and we react these building blocks. So it's all about the synthetic route, it's about the reaction, it's about the process design to then generate a product that is useful for humanity in all walks of life, from the time you wake up to the time you sleep, and even during the night, a chemical engineer is impacting on your life, whether it be the fertilizers, the food, the pharmaceuticals, the cleaning and hygiene issues, medical issues, electrical issues, fuel issues, transportation. Chemical engineers do apply to all walks of life here. So based on the core of what chemical engineering is, we pose these questions in terms of chemical engineering needs to understand the virtue of what we have at the moment. So it was about preserving the value of what we provide for society, but also add value in terms of creating new avenues to generate a better product that meets the SDGs. And at the same time, when we start looking at the fundamentals of this, we need to transform chemical engineering from an engineering discipline about the dynamics of movement of the raw material into the useful products, but integrated more within sciences so we can understand the fundamentals of how the raw materials are formed and how they can be shaped into building blocks, and then optimize the science processes within the engineering dynamic processes to then come up with a better understanding of how chemical engineering can impact better on society. And then we needed to impact on the world challenges, and globalization, economics, and environment are the three biggest elements that we have here. Where globalization is more integration, it's about generating wealth, which then features into economics. But then within this establishment, there's a demand on the environment in terms of using the raw materials, as well as the impact on the environment from the discharge that happens from the factories that we do here. So we needed to move the core elements of chemical engineering from a raw material upscaling to processing to products, and integrate more into science, innovation, engineering, and sustainability. So we wanted to address how science can enable us in a sustainable way to provide raw materials and upscale the raw materials to design a better process that has less demand on the environment and less impact on the environment in an innovative way, and at the same time generate the same products, if not generate new products and add more value to the economy of the system here. But then how do we impact the social element into the economic, society, and biosphere elements here? So we needed to look at the social elements in terms of the populations are increasing, and this adds to more demand on the raw materials, on the economy, and at the same time, the consumption or the insatiable consumption of energy, electricity, and water, and the discharge of emissions that happens here. And then we also had to understand that chemical engineering legacy is all about the petrochemicals, but with the finite existence of the resources and the movement away of the resources, we wanted to upscale into new materials as well and help our students become better prepared to use alternatives instead of just using the raw building blocks that we currently have here. And we also wanted the students to understand this diagram in the fact that we are taking resources from the environment to generate goods. And as we generate goods, a big chunk of what we take is generated as waste into the planet here as well. And when we address the sustainable goals, it's all about life under sea and above land. And it's about this integration of economy. It's about the equality. It's about the provision of the academics. So sustainability goes beyond efficiency and optimization in the fact that you have to integrate society and address how the raw materials are generated, used, utilized, and then how the emissions are going to impact on the system here. So it was a new paradigm in chemical engineering in terms of moving away from resources to production to products into using alternative raw materials such as the biological systems. And it's also about addressing how the impact of the availability of the resources, the environmental impact, and how we can add value in terms of generating the same quantities, if not higher quantities, from less raw material or less impacting raw material without emissions in a safer manner, adding value to the economy, reducing capital costs so more people can utilize and optimize their lifestyles, and at the same time, make sure we can recycle as much as we can. So the new objective of chemical engineering is to look at the grand challenges facing society here, apply them in terms of the industry interacting with us to educate society and help improve society while maintaining the sustainable goals in terms of water uses and resources uses and education in an innovative way, while maintaining the core of chemical engineering of upscaling raw material in a design process that generates products that interact in all walks of life. And to do this, we can't design the big scales that we have to do. So we have to integrate a lot more with the simulation and digitization elements, in the fact that we need to understand how the data is manipulated, how the behavior of the science can be upscaled into the processing. And we developed a lot of elements in terms of the sustainability of modeling these smaller scales, and then help integrate into, in terms of intensifications of flow chemistry, to then process into real life scenarios where we can take the new discoveries and add more values to the commercialization elements here. So basically, what we're trying to do is develop a better chemical engineer that takes in the new resources that are available here, address the sustainability in terms of using elements and how do they impact on the climate change here, and integrating the product into the process itself, and integrating that into the building blocks, into the raw material, and looking at the entire holistic systems here. So when it comes to the fundamental of the design, we need to keep the core of chemical engineering alive, because that is fundamentally what distinguishes chemical engineering from science and from other engineering disciplines. But we also wanted our students to be more interacted with the micro level as well as the macro level, understand what happens in the lab and how that transformation can happen for the better of society in terms of generating the products without actually, without actually relying on the resources. So it's about designing new processes that looks at the scientific backgrounds and help advance that in a better way. But we also wanted the students to be more interactive with the enterprising element, the innovation element, the economical elements here. And this then translates into looking at new raw resources and how does the chemical engineer transform these new resources into it, understanding the links with environmental engineering about the mitigation of our, instead of just dealing with the aftermath of pollution, is to actually look at the green chemistry element of things and how we can upscale other processes into reality and bring more innovative situations and solutions in our design to actually optimize our processes here. And this only happens with integration within industry. And that became a big element of what we're trying to do here. So the ethos of the course that I ended up designing here, it's about sustainability. I wanted to change the landscape of chemical engineering for a more sustainable future through the sustainable development goals here. And the first element is to break the sustainable goals and look at what they are. There's 17 of them, and integrated. So it's about the quality of education. It's about what Southampton stands for. And we are a Russell Group. We are number 13 in the UK in general. We're number 1 for chemistry research, number 5 for mechanical engineering and engineering research. We are in the top 70 around the world. So we had to design that quality element within us. And when we designed this course, we wanted to make sure there is equality in everything that we do here. So we widened the scope in terms of understanding STEMs, outreaching programs, making sure we include females and young students, as well as diverse members of society to interact within the course here. We also took the concept of the spheres that we developed from the core into integrating the raw materials and then the society and the education. And we looked at what chemical engineering is and the core of chemical engineering, as well as the depth and breadth, integrate with the design in this format, and it grows with you from 1 year to another year to another year. And another constraint that we had to look for is it's not that we designed a new course that will meet the requirements of society, but it's to design a course that will plug in a gap in terms of the lack of sustainable understanding within the chemical mentality, and then go further in terms of optimizing the resource. So we wanted to design for the long term, but design for the quality of the institute, design for the industry who's going to be using our graduates and our graduates to be shaping the future. But we also wanted a course that is accredited here. So in other words, we wanted to understand the smart manufacturing elements, look at the alternative resources coming in and how we can optimize these resources in terms of it, make sure everything that the students are studying is a multidisciplinary element that takes into account the economics, the legal issue, the ethical issues, the equality issues, biosphere, the economic impact, as well as the societal needs here. And we made sure we can digitize every element, because as societies move more towards data sciences and artificial intelligence and smart cities, we are starting to move towards a new realms, and we had to actually integrate that into it here. And we wanted to make sure our students can contribute to society in the most designed and optimized manner. So we've designed a course with accreditation in mind. We took the concept of the core of chemical engineering here and made sure we are plugging the gap between what scientists do and what engineers do to actually design better processes that are focused on sustainability, that reduces the waste, reduces the emissions, improve and optimize the upscaling of the raw material, look at the processing and how it interacts and how we can make things faster, cheaper, at a higher quality that meets the demands of society that needs here. And we made sure everything is integrated within the industrial locally as well as globally here. So the course we've designed, in green, we have the fundamentals of engineering. And then in orange, we have the fundamentals of chemistry and how that links in within the elements or the core of chemical engineering. Math obviously underpins everything and helps the students in terms of the digitization, in terms of the visualizations between simulation into processing reaction. All the blue elements are the core of chemical engineering, and it goes with them and grows with them in magnitude in terms of core, breadth, and depth as we go through it. And design for the future, design for sustainability, design for scale is integrated heavily within the course. And you can see this in part 4, part 3, where you have a big group design project, because we wanted the softer skills, we wanted the interaction, and we had the economy, we wanted the management, we want the law, we wanted the ethics, as well as the core element of chemical engineering. So it constitutes of 30% of the third year as a design project where you apply what you've learned in terms of a big project, featuring into your individual project, which represents 50% of your final year within the university. But we also made sure the economy is integrated as well as the society in terms of design for scale here, or commercialization as we refer to it. So the students can actually have the apply element in terms of it. And within the scope here in yellow, we put the electives, and the electives were all matched to the sustainable development goals here. And we've done the matrix instead of putting the 17 sustainable goals, look at the learning outcomes per each unit here and how we can then link between them and maintaining the core, the breadth and the depth of chemical engineering here. So we came up in terms of sustainable energy, in terms of water and wastewater use, sustainable chemistry, environmental biochemistry and new resources, ethics and engineering, pharmaceutical systems. And we took this further into the year 4, where the student has a breadth in terms of microscales, mesoscales, reducing the reactor size, reducing the operational size while maintaining the performances here. We went into waste and understand waste. We looked at bioenergy, energy resources, principles of applied energy and electrochemistry, machine learning and artificial intelligence, food processing, power plant safety. So we wanted to address all the Millennium Goals throughout this year. We also designed an MSc in terms of Advanced Sustainable Chemical Engineering. And you can see that we have a group design project, an MSc research project, as well as sustainability processing, as well as the core of chemical engineering. But we also selected some electives here that will help the student carve a pathway in terms of sustainability and how they can apply this here. But we didn't just focus on the design of the course here. We looked at the procurement, because I had the luxury of a pot of money to develop new labs. And developing the new labs, I've made sure sustainability was integrated throughout the process of procurement here. So we looked at the energy consumption, we looked at the background of the company, the carbon emissions, the impacts, the demands, and we started addressing this in terms of what we bought for the lab. As I said, chemical engineering and chemistry have had a facelift and a new dimension within Southampton, and it's 3-building complex with endless amount of labs and endless amount of 70 researchers and an array of PhD students. So we made sure that we designed the best optimum space for research and for teaching space, but at the same time that looks at the sustainable goals in terms of the use of gas emissions, energy, heating, utilization of chemicals, lighting. So we made sure sustainability is integrated in our building, as well as our course, as well as the labs that we use. And we have a large...
We're almost out of time.
Okay, I just need one more minute and then I will finish off here. So we've designed a labs. Okay, we'll skip this in terms of the labs here. We've made sure we have industrial partners. So we've coupled with all local industries as well as global industries, and in our industrial board, we have Shell, we have the large Pfizer's, we have AstraZeneca, we have financial banking systems, we have pharmaceuticals. We made sure they help us in design and then provide a pathway for our students to do. We also generated a new research center in terms of chemical engineering that will feature all these Millennium Goals in our research and scale-up elements here. So we made sure sustainability is interacted within our system here. We wanted to provide for our students to have a better job prosperity and meet the demands of the sustainable elements here. And at undergraduate, we've designed it. At postgraduate, we've designed it. Sorry, I've took too much time here.
It's okay. Thank you so much, Robert. That was amazing.
So please remember, if we all help and do a little bit, it will make a big difference.